Alright, now that we've explored how neural networks can predict numerical outcomes, we're going to shift our attention to a different type of problem. In this module, we focus on classification. Instead of predicting numbers, classification models predict categories. For example, determining whether an email is spam, identifying fraudulent transactions, or recognizing objects in an image. These are all examples of problems where the goal is not to estimate a value, but to decide which category something belongs to. What makes neural networks particularly powerful for classification is their ability to learn complex patterns in data, patterns that simpler models often struggle to capture. So in this module, we will connect what you already know about logistic regression and categorical outcomes to how deep neural networks perform classification tasks. We will explore how neural networks generate class predictions, how their outputs can represent confidence in those predictions, and how deeper networks can create more flexible decision boundaries that separate different categories. By the end of this module, you should have a clear understanding of how neural networks approach classification and why they are such powerful tools for solving real-world prediction problems. Before diving deeper into neural networks for classification, it helps to connect this idea to something you may already be familiar with: logistic regression. Logistic regression is one of the most common traditional methods used for classification problems. Instead of predicting a numerical value, the model estimates the probability that an observation belongs to a particular category. For example, a logistic regression model might estimate the probability that an email is spam or the probability that a financial transaction is fraudulent. If that probability crosses a certain threshold, the model assigns the observation to a specific class. Now, here's the important connection. Deep neural networks perform classification in a very similar conceptual way. They also transform input data into probabilities that represent how likely an observation belongs to each possible class. The difference is that neural networks can learn much more complex relationships between inputs and outcomes. Instead of relying on a single transformation like logistic regression, neural networks apply multiple layers of transformations. These layers allow the model to capture patterns that are nonlinear, high-dimensional, and often difficult to describe explicitly. So you can think of neural network classification as an extension of the same idea behind logistic regression, but with far greater flexibility and learning capacity. Now let's look at how a neural network actually produces a class prediction. When we feed data into a neural network, the inputs do not immediately become predictions. Instead, the data moves through multiple layers of neurons inside the network. Each layer performs a transformation on the information it receives. As the data moves forward through these layers, the network gradually learns to detect patterns and relationships within the data. These hidden layers are where most of the learning happens. They transform the raw inputs into more meaningful internal representations. Eventually, the data reaches the output layer. In a classification problem, the output layer converts the learned representation into class probabilities. Each probability represents how likely the model believes the input belongs to a particular category. Finally, the network chooses the class with the highest probability as its prediction. So the overall process is simple in concept. Inputs move through layers, patterns are learned, probabilities are produced, and the most likely class becomes the model's final prediction. Now let's talk about decision boundaries. In many traditional classification models, the separation between classes is often represented by a straight line, or in higher dimensions, a flat plane. These are called linear decision boundaries. Linear boundaries work well when the data can be separated in a relatively simple way. But in many real-world problems, the relationship between variables is far more complicated. Classes may overlap, curve around each other, or form patterns that cannot be separated with a single straight boundary. This is where deep neural networks become especially powerful, because neural networks apply multiple layers of transformations. They can gradually reshape the representation of the data. Each layer helps the model capture more complex structure in the input. The result is that deep networks can form flexible, nonlinear decision boundaries. These boundaries can bend, curve, and adapt to the structure of the data, allowing the model to separate classes even when the patterns are highly complex. Now, let's look at the difference between binary classification and multi-class classification. In a binary classification problem, there are only two possible outcomes. The model's task is to decide which of those two categories an observation belongs to. A common example is spam detection. An email is either classified as spam or it is not. Many real-world problems, however, involve more than two categories. These are known as multi-class classification problems. For example, when recognizing handwritten digits, the model must decide whether an image represents a 0, 1, 2, 3, all the way through 9. The key idea here is that neural networks adjust the structure of the output layer, depending on the task. For binary classification, the network typically produces a single probability representing the likelihood of one class. For multi-class problems, the network produces multiple probabilities, one for each possible category, and the class with the highest probability becomes the prediction. Now let's discuss something that is unavoidable in classification models: errors. No model is perfect, and classification systems can make mistakes. Two of the most common types of mistakes are called false positives and false negatives. A false positive occurs when the model predicts that a condition is present, even though it is not. For example, a spam filter might incorrectly classify a legitimate email as spam. A false negative, on the other hand, occurs when the model fails to detect a condition that actually exists. For example, a medical screening model might fail to identify a disease that is truly present. These two types of errors can have very different consequences, depending on the application. In some situations, false positives may be more acceptable. In other cases, false negatives can be far more serious. Because of this, evaluating classification models is not just about overall accuracy, it also involves understanding which types of errors occur and how costly they are in real-world decisions. Finally, let's talk about an issue that often has a major impact on classification performance: the quality of the data. Even a well-designed neural network can struggle if the training data contains certain problems. Two of the most common issues are class imbalance and noisy labels. Class imbalance occurs when one category appears far more often than the others in the dataset. For example, in fraud detection, fraudulent transactions may represent only a very small percentage of all transactions. When this happens, a model may become biased toward predicting the majority class, simply because it sees that class much more frequently during training. Another challenge is noisy labels. Noisy labels occur when observations in the dataset are incorrectly labeled. For example, an image labeled as one object might actually belong to a different category. When labels are inconsistent or incorrect, the model may learn misleading patterns, which can reduce its reliability and predictive performance. Because of this, successful classification systems depend not only on the model itself, but also on carefully prepared, high-quality training data. In Cell 2, this is our setup step. Here we load all the tools we'll need for the entire notebook. We bring in libraries for working with data, making plots, splitting the data set into training and testing sets, scaling the inputs, and evaluating a classification model. Then we load TensorFlow and Keras, because that's what we'll use to build a deep neural network. And at the end of this cell, we print a TensorFlow version, just to confirm the environment we're running in. Now in cell 3, we upload the dataset into Google Colab. This step opens the upload widget, and when we select the file, Colab stores it in the current session. The notebook then prints the uploaded file name, so we can verify that the dataset is actually available before we try to load it. Next, in cell 4, we load the data. We read the CSV file into a data frame, which gives us a clean table we can work with. Then we immediately do 2 quick checks. We print the shape, so we know how many rows and columns we have. And we display the first few rows just to confirm the data loaded correctly and the columns look like what we expect. And now in cell 5, we do basic data sanity checks. We inspect the dataset structure to confirm the columns and data types. Then we check for missing values across the dataset, because missing data can quietly break modeling steps later. After that, we check for duplicate rows, which can bias results if the same record appears more than once. And finally, we look at the target variable, churn, to see how many cases are churn versus non-churn. That class distribution matters a lot in classification, because if one class is rare, we need to be careful about how we evaluate performance. Now, let's continue. In cell 6, we prepare the dataset for modeling. Here we select only the variables that the assignment requires. Specifically, we keep 4 predictor variables: tenure, age, income, and education, along with the target variable, which is churn. By creating a new dataset with only these columns, we simplify the modeling process and make sure the neural network only sees the features we intend to use. This cell also ensures that the churn variable is stored as a binary integer, meaning a values of 0 and 1. That's important because classification models expect the target variable to be represented in a clear numeric format. Finally, we display summary statistics for these columns so we can quickly see things like the average values, ranges, and general scale of each variable. Next, in cell 7, we start exploratory data analysis using histograms. For each predictor variable, we create a histogram that shows how the values are distributed across the dataset. This allows us to see whether the variables are evenly spread, skewed towards certain ranges, or contain unusual patterns. Visualizing distributions like this is useful before modeling because it helps us understand the basic shape of the data we are working with. Then in cell 8, we compare these variables across churn groups using box plots. Instead of looking at the entire dataset together, this step separates customers who churned from those who did not. For each predictor variable, we generate a box plot that shows the distribution for the non-churn group and the churn group side by side. This makes it easier to see whether certain variables appear to differ between the two groups, which could indicate that those variables might help the model predict churn. In cell 9, we examine the class balance of the dataset. Here we count how many customers fall into each category, those who churned and those who did not. The result is displayed as a bar chart, so we can visually compare the sizes of the two groups. The cell also prints the proportions of each class. This step is important because if one class heavily dominates the dataset, it can affect how well a classification model learns to detect the minority class. Finally, in cell 10, we examine relationships among the predictor variables using a correlation heat map. This visualization shows how strongly each feature is related to the others. Strong correlations between predictors can indicate redundancy in the dataset, which sometimes causes issues such as multicollinearity. By inspecting the heat map, we can quickly identify whether any variables move closely together and might carry similar information. Together, these steps give us a clear understanding of the dataset before we begin training the neural network. We've selected the relevant variables, explored their distributions, compared them across churn groups, checked the class balance, and examined relationships among the predictors. In cell 11, we check for multicollinearity using something called the variance inflation factor, or VIF. The idea here is to see whether any of the predictor variables overlap too heavily with each other. If two predictors carry almost the same information, they can interfere with certain statistical models. This step calculates a VIF score for each feature and displays them in a table so we can quickly see if any values are unusually high. If the scores stay reasonably low, it means that predictors are not strongly redundant. Next, in cell 12, we perform an informal distribution check using QQ plots. For each predictor variable, we generate a plot that compares the observed data distribution to a normal distribution. The goal here isn't to enforce strict normality. Neural networks and logistic regression don't require that. Instead, this is simply a visual way to spot strong skewness or extreme outliers that might affect how the model learns from the data. Then in cell 13, we perform a quick outlier scan using z-scores. Here we measure how far each observation lies from the mean of its variable, expressed in standard deviations. As a simple rule of thumb, values that are more than 3 standard deviations away from the mean are often considered potential outliers. This step counts how many such extreme observations exist for each feature and prints a small summary. It doesn't remove anything yet. It simply helps us understand whether unusual values might be present. Finally, in cell 14, we perform a diagnostic check related to logistic regression assumptions. One common assumption in logistic models is that continuous predictors have an approximately linear relationship with the log odds of the outcome. To explore this, we divide each predictor into bins, compute the churn rate within each bin, and then transform that rate into log odds. By plotting these values, we can visually inspect whether the relationship between each predictor and the log odds of churn appears roughly linear. This step doesn't enforce anything automatically. It simply gives us a visual diagnostic so we can judge whether the predictors behave in a way that aligns with logistic modeling assumptions. So at this point in the notebook, we've completed a fairly thorough exploratory and diagnostic phase. We've inspected distributions, checked class balance, examined correlations among predictors, looked for multicollinearity, scanned for potential outliers, and performed a quick check related to logistic style modeling assumptions. All of these steps help ensure that the dataset is well understood before we move on to building and training the classification model. Now, in cell 15, we split the dataset into training and testing sets. At this point, we separate the predictor variables from the target variable so the model knows what information it can use to make predictions and what outcome it should try to learn. Then we divide the dataset into 2 parts, one portion for training the model and another portion for testing its performance later. About 75% of the data is used for training and the remaining 25% is reserved for testing. The split also keeps the churn proportion consistent across both sets, so the class balance remains similar. After the split, the notebook prints the shapes of the training and testing datasets along with the churn rates in each set, just to confirm that the split worked as expected. Next, in cell 16, we scale the predictor variables. Neural networks tend to train more efficiently when input features are on similar numerical scales. So here we standardize the predictors by centering them around 0 and scaling them so they have roughly unit variance. Importantly, the scaling parameters are learned only from the training data and then applied to the test data. This prevents information from the test set from leaking into the training process. The cell also prints the approximate means and standard deviations of the scaled training data to verify that the transformation worked correctly. Then in cell 17, we build the neural network model. Here, we define a sequential neural network architecture. The model begins with an input layer that matches the number of predictor variables, followed by two hidden layers that learn intermediate patterns in the data using a nonlinear activation function. The final layer produces a single output value between 0 and 1, representing the predicted probability that a customer will churn. After defining the structure of the network, we compile the model by specifying the optimization algorithm, the loss function appropriate for binary classification, and evaluation metrics such as accuracy and the area under the ROC curve. Finally, the notebook prints a summary of the model architecture so we can see how the layers are connected. Finally, in cell 18, we train the neural network. Before training begins, an early stopping rule is defined. This mechanism monitors validation performance during training and stops the process automatically if the model stops improving. That helps prevent overfitting and ensures we keep the best version of the model. The training process then begins using the scaled training data. A portion of the training data is set aside internally for validation so we can track performance during learning. The model is trained for up to 200 epochs using small batches of observations at a time. As training progresses, the notebook displays the learning progress for each epoch, including how the loss and evaluation metrics evolve. At this point, the neural network has learned patterns from the training data and is ready to be evaluated on unseen test data. Now in cell 19, we visualize the training process. After training the neural network, the model keeps a history of how its performance changed during learning. In this step, we plot several training curves so we can see how the model behaved across the epochs. The first plot shows how the loss changed over time for both the training data and the validation data. Ideally, we want to see the loss decrease as training progresses, and we want the training and validation curves to stay relatively close to each other. If the training loss continues decreasing while the validation loss starts increasing, that can be a sign of overfitting. The second plot shows how classification accuracy evolves during training, again comparing training accuracy with validation accuracy. This helps us see whether the model is actually improving its predictions as it learns. The final plot shows the AUC score over the training epochs. AUC measures how well the model separates the churn and non-churn classes across different probability thresholds. Watching this metric during training gives us another perspective on the model's ability to distinguish between the two groups. Together, these three plots provide a visual summary of how the neural network learned over time. Next, in cell 20, we evaluate the trained model on the test set. Up to this point, the model has only seen the training data. Now we measure its performance on completely unseen data, the test set. The evaluation step computes three metrics: the loss value, the classification accuracy, and the AUC score. These metrics give us a clearer picture of how well the model generalized beyond the data it was trained on. Finally, in cell 21, we generate predictions and examine the classification results. Here, the trained model produces probability predictions for each observation in the test set. Those probabilities are then converted into binary class predictions using a threshold of 50%. In other words, if the predicted probability of churn is at least 0.5, the observation is classified as churn. Otherwise, it is classified as non-churn. Once those predictions are generated, we compute several evaluation outputs. First, we calculate the overall classification accuracy. Then we print a classification report, which provides more detailed metrics such as precision, recall, and the F1 score for each class. Finally, we generate the confusion matrix, which summarizes how many observations were correctly classified and how many were misclassified in each category. At this point, the entire workflow is complete. We've explored the dataset, prepared the features, trained a deep neural network classifier, monitored the learning process, and evaluated how well the model performs on unseen data. Now, in Cell 22, we create a visual version of the confusion matrix. Earlier, we printed the confusion matrix as numbers, but numbers alone can be difficult to interpret quickly. So here, we generate a graphical version of the confusion matrix. Each cell of the matrix represents the number of observations that fall into a specific prediction category: correct non-churn predictions, correct churn predictions, and the two types of classification errors. By visualizing this as a heat map style plot, it becomes much easier to see where the model performs well and where it struggles. Next, in Cell 23, we plot the ROC curve. The ROC curve is one of the most common tools used to evaluate binary classification models. It shows the trade-off between the true positive rate and the false positive rate as the classification threshold changes. Instead of relying on a single cutoff value, this curve lets us see how well the model separates the two classes across all possible thresholds. The area under this curve, the AUC, summarizes that performance with a single number. A value closer to 1 indicates that the model can distinguish churners from non-churners more effectively. Finally, in Cell 24, we create two visualizations that help us understand the model's probability predictions. The first plot compares predicted churn probabilities with the actual outcomes. Since the true labels are only 0 or 1, we slightly jitter the actual values so the points don't overlap perfectly. This makes it easier to see whether the model tends to assign higher probabilities to customers who actually churned and lower probabilities to those who did not. The second plot shows the distribution of predicted probabilities. This histogram helps us see how confident the model tends to be in its predictions. For example, we might observe a cluster of predictions near 0 or near 1, or we might see many predictions near the middle if the model is uncertain. At this point, the workflow is complete. We've moved from loading the dataset, exploring and preparing the features, training a deep neural network classifier, and finally evaluating its performance through multiple metrics and visualizations.